Across a gulf of space so profound that the light traversing it has been stretched and reddened by the very expansion of the universe, there exists a point of incandescence. It does not resolve into a spiral arm or a galactic core, not through the most powerful optical instruments devised. It remains a stellar point, a quasi-stellar object, a quasar, catalogued as TON 618. This designation, born from the Tonant-Sintla Observatory survey in the mid-20th century, belies the entity's true nature. It is not a star, nor is it a nearby object of modest power. It is a beacon lit in a distant past, its photons having traveled for an estimated 104 billion years to reach us, a journey that began when the cosmos itself was less than a quarter of its current age. The light from TON 618 is not merely bright, it is a monument to energetic release, shining with a luminosity calculated to be 140 trillion times that of our own Sun. This is a radiance that defies simple comparison, an output equivalent to thousands of Milky Way galaxies combined, all emanating from a region of space smaller than a single solar system. And yet, the source of this impossible furnace is not light, but its perfect antithesis. The engine driving this cosmic lighthouse is an object of pure gravity, a supermassive black hole of such scale that it challenges the very models of galactic and cosmological evolution. The implicit question carried by every photon from this distant point is not simply what it is, but how such a thing could possibly come to be. It represents a concentration of mass so extreme, a gravitational authority so absolute, that it has ignited the space around it into a furious blaze, an inferno visible across more than 10 billion light-years of expanding spacetime. The faint, unassuming point of light is a veil, a brilliant distraction from the silent, invisible sovereign that commands it, a gravitational singularity of 66 billion solar masses, the most massive black hole yet discovered, a true titan of the early universe whose existence poses fundamental questions about the upper limits of physical structure and the processes that govern the cosmos in its turbulent youth. It is a ghost of a fire that raged when the universe was young, and the object that lit it remains, a quiet gravitational shadow of almost incomprehensible scale. Within this distant beacon, the light we observe is not generated by the black hole itself, for from beyond its event horizon, nothing, not even light, can escape. The prodigious luminosity of TON 618 is instead the final, violent testament of matter succumbing to this immense gravitational pull. Surrounding the central darkness is an accretion disk, a vast, flattened swirl of gas, dust, and the shredded remnants of stars, all spiraling inward toward their ultimate annihilation. This is not a gentle cosmic whirlpool, it is a region of unimaginable friction and compression. As material from the host galaxy is drawn into this gravitational vortex, its angular momentum forces it into a disk that orbits the black hole at relativistic speeds, with particles and gas clouds moving at significant fractions of the speed of light. The inner edges of this disk are a place of physical extremes. Frictional forces between adjacent, differentially rotating layers of gas generate colossal amounts of heat, raising the temperature of the plasma to millions of degrees Kelvin. The matter is no longer merely hot, it is incandescent, stripped down to its constituent atomic nuclei and electrons, glowing with an intensity that outshines all the stars of its host galaxy combined. This superheated material radiates energy across the entire electromagnetic spectrum, from low-energy radio waves to the most energetic gamma rays. The light we see, the 140 trillion solar luminosities, is the collective death cry of countless tons of matter per second being converted into pure energy according to the principles of mass-energy equivalence. The accretion disk of TON 618 is itself a structure of galactic proportions, likely extending for light-years, a swirling plane of fire where gravitational potential energy is relentlessly and efficiently transformed into radiation. The brilliance of the quasar is therefore a direct measure of the black hole's feeding rate, a reflection of the sheer quantity of interstellar material it is consuming. This process is a delicate and violent balance. The very radiation produced by the infalling matter exerts an outward pressure, a wind of light that pushes against the incoming fuel, setting a natural limit on how fast a black hole can grow. TON 618 appears to be operating at or very near this theoretical maximum, the Eddington limit, consuming matter with an almost perfect, voracious efficiency that allowed it to achieve its titanic mass in the relatively short span of cosmic time available in the early universe. The light is a byproduct, a symptom of a gravitational process so powerful it has turned the space around it into the most luminous sustained object in the known cosmos. Beneath the swirling, incandescent fury of the accretion disk lies the object responsible for the entire phenomenon, the central singularity of TON 618. This is not an object in the conventional sense, not a sphere of matter or a solid surface, but a rupture in the fabric of spacetime itself. All of its 66 billion solar masses, a quantity of matter equivalent to a medium-sized galaxy, are compressed by their own gravity into a region of theoretically infinite density. This is the ultramassive black hole, a gravitational monarch whose dominion is defined not by what it is, but by the boundary it enforces upon reality. This boundary is the event horizon, a perfect, spherical surface of no return. For TON 618, this horizon is a region of space of almost unbelievable size, a testament to the direct relationship between mass and the scale of spacetime distortion. According to the laws of general relativity, the presence of this immense mass fundamentally alters the geometry of the universe around it. Spacetime is no longer a passive backdrop but is warped into a steep, inescapable gravitational well. The event horizon marks the precise distance from the singularity where the curvature of spacetime becomes so extreme that all possible paths for matter and energy, including light itself, curve inward. Once this threshold is crossed, the future of any particle or photon is a single point, the singularity at the center. The black hole at the heart of TON 618 is thus a perfect void, an absolute blackness defined by the light it commands but can never emit. We infer its presence and its properties indirectly, through the precise orbital mechanics of the material in the accretion disk and the gravitational lensing of light from objects behind it. Its mass is not measured by seeing it, but by calculating the gravitational force required to bind the furiously orbiting gas clouds and to produce the observed luminosity. It is a negative presence, an absence that organizes and powers a system of cosmic scale. Compared to the supermassive black hole at the center of our own Milky Way, Sagittarius A, which contains the mass of 4 million suns, TON 618 is more than 15,000 times more massive. It is an entity that belongs to a different class of cosmic objects, an ultramassive black hole that represents the upper echelon of gravitational structures, formed and fed in the uniquely dense and chaotic environment of the early cosmos. Its existence is a silent, enduring testament to gravity's ultimate power to shape, to command, and to erase. To comprehend the physical scale of TON 618's domain is to confront a size that challenges terrestrial and even astronomical intuition. The size of a black hole is not its physical volume in the classical sense, but the radius of its event horizon, the so-called Schwarzschild radius. This radius is directly proportional to its mass. For an object weighing 66 billion solar masses, this calculation yields an event horizon with a radius of approximately 1,300 astronomical units, AU, where 1 AU is the average distance from the Earth to the Sun. This means the diameter of TON 618's event horizon spans roughly 2,600 Australian dollars. To place this in a familiar context, one must consider the architecture of our own solar system. The orbit of Neptune, the most distant planet, is about 30 Australian dollars from the Sun. The dwarf planet Pluto follows an elliptical path that takes it out to nearly 50 Australian dollars. The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object, has traveled for nearly half a century and is currently about 160 Australian dollars from the Sun. All of these distances, the entire planetary region of our solar system, would fit comfortably inside the radius of TON 618's event horizon thousands of times over. The boundary of our solar system is often considered to be the heliopause, where the Sun's solar wind is stopped by the interstellar medium, a frontier Voyager 1 crossed at about 121 Australian dollars. Even this vast magnetic bubble is dwarfed by the black hole. The true scale becomes even more apparent when considering the Oort cloud, the theoretical spherical shell of icy planetesimals that is thought to surround our Sun at distances ranging from 2,000 to 200,000 Australian dollars. The inner edge of the Oort cloud would lie just outside the event horizon of TON 618. An observer situated at the position of our Sun would see a perfect, featureless black sphere that fills a significant portion of the sky, an abyss whose edge is farther away than the most distant, hypothetical comets of our own system. Light from one edge of this event horizon would take more than 15 days to travel to the other side. This is not a planetary-scale object, it is a stellar system-scale object, a single, cohesive gravitational entity whose sphere of absolute influence is larger than the familiar map of our entire cosmic neighborhood. The sheer volume of spacetime enclosed by this boundary is staggering, a region from which no information can ever escape, a silent, black sphere larger than many nebulae, all governed by the compressed mass of a galaxy collapsed into a single point. This geometric finality, this perfect sphere of blackness, is the true face of TON 618, hidden beneath the glare of its accretion disk. The remote and abstract nature of such a cosmic object is grounded in the tangible data collected by telescopes, in the subtle signatures encoded within the light that has traveled across billions of years of cosmic history. The spectrum of a quasar, the rainbow of its light broken down into constituent wavelengths, is not a smooth continuum. It is a landscape of peaks and valleys, of emission and absorption lines, which act as fingerprints of the chemical elements present in the quasar's environment and their physical conditions. For TON 618, one of its most defining spectral features is the presence of unusually broad absorption lines. An absorption line is created when light passes through a cooler gas, and atoms within that gas absorb photons of specific energies, creating dark bands in the spectrum. The width of these lines reveals information about the motion of the gas. If the gas is stationary, the lines are narrow and sharp. If the gas is moving, the lines are broadened by the Doppler effect. Gas moving towards the observer shifts the absorption to bluer, higher energy wavelengths, while gas moving away shifts it to redder, lower energy wavelengths. In the case of TON 618, the absorption lines are immensely broad, indicating that the absorbing gas is not a placid cloud but a turbulent, high-velocity outflow. These spectral signatures are evidence of powerful winds being driven away from the accretion disk. The intense radiation pressure from the disk, the same force that sets the Eddington limit, is so powerful that it can accelerate vast clouds of gas to extraordinary speeds, ejecting them from the black hole's immediate vicinity. The broadening of the lines in TON 618 spectrum suggests outflow velocities reaching up to 7,000 km per second, a significant fraction of the speed of light. These are not gentle breezes but cataclysmic outflows of matter, carrying away mass from the accretion disk in quantities that may rival the rate at which matter is being consumed by the black hole itself. This process, known as quasar feedback, is a critical mechanism in the evolution of galaxies. The energy and matter blasted out by the central quasar can heat and expel the gas from the host galaxy, quenching star formation and regulating the galaxy's growth. The broad absorption lines of TON 618 are therefore more than a spectral curiosity, they are the direct, observable evidence of this powerful feedback mechanism in action. They are the signature of the quasar's immense power actively shaping its environment, a testament to the dynamic and often destructive interplay between a supermassive black hole and the galaxy that sustains it. We see not just the light of infalling matter, but the shadow of matter being violently expelled, a cosmic battle between gravity and radiation written in the language of light. A quasar like TON 618, with its ultramassive central engine and voracious appetite, cannot exist in isolation. It must reside at the heart of a host galaxy, a vast reservoir of the gas, dust, and stars that serve as its fuel. While the overwhelming glare of the quasar itself makes direct observation of its host galaxy exceptionally difficult, theoretical models and observations of less luminous quasars provide a clear picture of the necessary environment. The host galaxy of TON 618 must be one of the most massive and gas-rich galaxies of its epoch. Such a galaxy would not be a delicate spiral like our own Milky Way, but likely a giant elliptical galaxy or the chaotic, disturbed remnant of a recent major merger between several large galaxies. The formation of a 66 billion solar mass black hole requires a near-constant and incredibly efficient supply of fuel over hundreds of millions of years. This is a process that is thought to be triggered and sustained by the gravitational disruption of galactic collisions. When two large, gas-rich galaxies merge, their interstellar gas clouds are thrown into disarray. Gravitational torque stripped the gas of its angular momentum, causing it to lose energy and plummet towards the newly merged galactic center. This catastrophic inflow of cold gas provides the perfect fuel source for the central supermassive black hole, igniting it as a brilliant quasar. The era in which we observe TON 618, roughly 34 billion years after the Big Bang, corresponds to a period in cosmic history known as cosmic noon. This was a time of peak star formation and frequent galactic mergers, an era when galaxies were more compact and gas-rich than they are today, providing the ideal conditions for the rapid growth of supermassive black holes. The host galaxy of TON 618 would therefore be a crucible of cosmic activity, a site of rampant starbursts and gravitational chaos, all while its central monster grew at an almost unimaginable rate. The relationship between the black hole and its host is now understood to be deeply symbiotic, a process of coevolution. The mass of a central black hole is observed to be tightly correlated with the mass and velocity dispersion of the stars in its host galaxy's central bulge. This suggests that the same processes that build the galaxy also build the black hole, and that the feedback from the quasar, in turn, regulates the growth of the galaxy by clearing out its gas. TON 618 represents an extreme, outlier case in this relationship, a black hole that seems almost too large for its era, suggesting a history of exceptionally efficient accretion, perhaps enabled by a series of perfectly timed and exceptionally massive galactic mergers. It is a product of a violent and fertile environment, a gravitational jewel formed under the immense pressures of a young and turbulent universe. The immense distance to TON 618 fundamentally alters our perception of it, transforming it from a contemporary object into a relic from a bygone cosmic age. The finite speed of light dictates that looking out into space is equivalent to looking back in time. The light we capture today from this quasar began its journey 104 billion years ago. During its immense voyage, the universe has expanded, aged, and evolved. The cosmos it traversed was younger, denser, and hotter than the one we inhabit. When these photons were emitted, our own solar system did not exist. The Sun and its planets would not form for another 6 billion years. The Milky Way galaxy itself was in a much earlier stage of its development. We are therefore not observing TON 618 as it is now, but as it was during the cosmic noon, a frenetic period of cosmic construction. This look-back time provides a unique window into the physics of the early universe, allowing astronomers to study a class of objects that no longer exists in our local cosmic neighborhood. The quasar era has largely passed. The universe has expanded, galaxies have settled, and the copious fuel supplies that fed these luminous behemoths have been mostly consumed or blown away. The intense quasar activity peaked when the universe was between 2 and 4 billion years old and has declined precipitously since. Today, most massive galaxies, including our own, harbor dormant supermassive black holes at their centers. They are quiescent, starved of fuel, and only occasionally flare up when a stray star or gas cloud wanders too close. It is overwhelmingly likely that TON 618, as an active quasar, has been extinct for billions of years. The object we see burning with the light of 140 trillion suns is, in the present day, almost certainly a dark and silent entity. Its host galaxy, having had its gas reserves scoured by the quasar's feedback winds, is probably now a red and dead, elliptical galaxy, populated by old, red stars with little to no new star formation occurring. The ultramassive black hole, now weighing even more than its observed 66 billion solar masses after billions of years of potential further consumption, would sit silently at its center. Our observation is an archaeological one. We are seeing a fossil, a preserved image of a cosmic firestorm that has long since subsided. The light is an echo, a ghost of a past glory, carrying with it the story of a universe that was once far more violent, compact, and incandescent than the comparatively placid cosmos of the present. The study of TON 618 is the study of our own cosmic history, a glimpse into the formative, fiery adolescence of the universe itself. The existence of a black hole as massive as TON 618 so early in the universe's history strains our models of black hole formation and growth. There is a fundamental physical constraint on how quickly a black hole can accrete matter, known as the Eddington limit. This limit arises from the balance between the inward pull of gravity and the outward push of radiation pressure. As matter falls into the accretion disk, it heats up and radiates energy. This radiation, composed of photons, carries momentum and exerts a pressure on the surrounding gas. If the luminosity of the accretion disk becomes too high, the resulting radiation pressure will be strong enough to halt the inflow of new material, effectively choking off the black hole's fuel supply. This creates a self-regulating feedback loop that imposes a theoretical maximum growth rate. For a black hole to grow from a stellar mass seed, the remnant of a massive star's collapse, to 66 billion solar masses in the few billion years available since the Big Bang, it would need to accrete matter at or very near its Eddington limit, continuously, for its entire existence. This scenario is considered highly improbable. It requires a sustained, perfectly channeled flow of gas into the galactic nucleus, a condition difficult to maintain amidst the chaotic dynamics of galaxy formation. This has led to alternative theories for the formation of such ultramassive black holes. One possibility is the direct collapse of massive primordial gas clouds. In the early universe, before the first stars had enriched the cosmos with heavy elements, truly enormous clouds of pure hydrogen and helium could have existed. Under certain conditions, a cloud with the mass of hundreds of thousands of suns might have been able to collapse directly into a massive black hole seed, bypassing the stellar evolution phase entirely. This would give the black hole a significant head start, making it easier to reach ultramassive status by the time we observe TON 618. Another possibility involves hierarchical mergers. Instead of growing solely through gas accretion, a black hole could grow by merging with other black holes. In the dense core of a forming galaxy, numerous stellar mass and intermediate mass black holes could form and sink to the center via dynamical friction, where they would coalesce into a larger and larger object. TON 618 might be the product of a long history of such mergers, the final victor in a gravitational battle royale at the heart of a protogalaxy. It is likely that both mechanisms, sustained, super-Eddington accretion episodes and a history of mergers, played a role. TON 618 sits at the very edge of what our current theories can explain, a data point that forces a re-evaluation of the processes that assemble the largest bound structures in the cosmos. It is a beautiful problem, an object whose sheer scale demands a deeper understanding of the interplay between gravity, radiation, and the evolution of cosmic structure. Even an entity as seemingly eternal and indestructible as the ultramassive black hole at the center of TON 618 is subject to the subtle and patient laws of quantum physics and will eventually meet its end. While classical general relativity describes black holes as immortal prisons of matter and energy, the introduction of quantum mechanics paints a different picture. In the 1970s, Stephen Hawking demonstrated that when quantum effects are considered near the event horizon, black holes are not entirely black. They should emit a faint thermal radiation, now known as Hawking radiation, due to the creation of virtual particle-antiparticle pairs in the quantum vacuum at the edge of spacetime. Occasionally, one particle of a pair falls into the black hole while the other escapes, carrying away a tiny amount of energy. To an outside observer, this appears as if the black hole is radiating and, by the law of mass-energy equivalence, slowly losing mass. This process of evaporation is extraordinarily slow, and its rate is inversely proportional to the black hole's mass. The more massive the black hole, the colder it is and the more slowly it evaporates. For a stellar mass black hole, the time to evaporate is already vastly longer than the current age of the universe. For a supermassive black hole like Sagittarius A, the timescale is on the order of 10 to the power of 87 years. For TON 618, with its 66 billion solar masses, the calculation yields a number so large it beggars belief. The estimated time for TON 618 to completely evaporate through Hawking radiation is approximately 10 to the power of 100 years, a duration known as a Google years. This timescale is so far beyond any familiar cosmic or human scale as to be functionally infinite. It is a number far larger than the number of atoms in the observable universe. The process would begin imperceptibly slowly. For the first many trillions of years, during the stelliferous era, it will continue to accrete matter from the cosmic microwave background and interstellar medium, growing slightly rather than shrinking. Only when the universe has expanded and cooled to near absolute zero, when all stars have burned out and all galaxies have dispersed, in the deep, dark, cold future known as the black hole era, will the process of evaporation dominate. Over googolls of years, TON 618 will slowly shed its mass, photon by photon, its temperature gradually rising as its mass decreases, culminating in a final, brief flash of high-energy particles as the last remnant of its mass disappears. Its ultimate fate is to dissolve back into the universe as a whisper of thermal radiation, its immense gravitational legacy erased, leaving behind only an expanded and emptier spacetime. This final act places the awesome power of TON 618 in the grandest of all cosmic perspectives, as a magnificent but ultimately transient structure in the long, unfolding story of the cosmos. Returning, then, to the single, unassuming point of light in the constellation of Canes Venatici, its meaning is now transformed. It is no longer a simple star or a distant celestial object, but a portal through time, a deeply layered narrative written in the language of physics. That faint photon, captured on a detector after a journey of more than 10 billion years, carries within its frequency and polarization the story of its origin in a crucible of unimaginable violence. It speaks of a disk of plasma hotter than the core of a star, of matter accelerated to relativistic speeds, and of a gravitational engine 15,000 times more massive than the one at our own galactic center. It is an artifact from the age of Titans, when the universe was young and furiously building the structures that would define its future. The light is a testament to the power of gravity to organize matter on the grandest scales, to take the diffuse gas of a primordial galaxy and focus it into a point of such density that it rips the fabric of spacetime, igniting the surrounding void into a beacon visible across the observable universe. Yet, it is also a story of limits and feedback. The broad absorption lines etched into its spectrum tell of the inevitable response, of radiation pushing back against gravity, of galactic winds that sculpt the host galaxy and regulate its growth, ensuring that no single object can consume everything. The existence of TON 618 pushes our understanding of these limits, suggesting that under the unique conditions of the early cosmos, growth could be far more efficient and rapid than previously thought. And finally, the light is an echo. The fire that forged it has almost certainly died out billions of years ago. The object we witness in its brilliant youth is now a silent, dark relic, presiding over a mature galaxy, its period of glorious consumption long past. Its story arcs from a violent, luminous birth, through a long and quiet middle age, to an impossibly distant and gentle death through the slow quantum fizz of Hawking radiation. What began as a point of light is revealed to be a monument to scale, time, and the intricate, self-regulating laws that govern the cosmos. It is a reminder that the universe contains structures of a magnitude that defy easy comprehension, and that even the most powerful and seemingly eternal of these are but temporary configurations in the endless flow of cosmic evolution. The single photon is a messenger from a lost epoch, and the message it carries is one of epic creation, silent persistence, and an ultimate, quiet dissolution into the void.